There is a widely accepted operational axiom in modern cloud architecture. To serve large language models efficiently, you must split the compute-intensive prefill phase from the memory-intensive decode phase. This is known as disaggregation. But physically, this separation remains extremely restrictive. During the prefill phase, a model generates a massive block of contextual memory, known as the KVCache. If you separate your prefill and decode hardware, that cache creates a massive data tether. You have to transport the entire state across the network instantly. This tether creates what engineers call the RDMA Prison. To keep the prefill decode pipeline functioning without stalling the GPUs, architects are forced to source scarce, highly specialized hardware and lock it all within a single, tightly coupled data center connected by low-latency RDMA fabrics. You cannot mix and match chips across regions, and you cannot leverage cheaper commodity hardware. But that KVCache tether is no longer an immutable physical constraint. Breaking this hardware lock-in relies on a shift in how models construct attention, paired with a routing layer that manages exactly when and where data moves. The primary obstacle keeping models locked in single data centers is the bandwidth wall. We quantify this by looking at the KV throughput of conventional dense attention architectures. This chart tracks KV cache generation at a 32,000 token context window. A single instance of a dense model like Minimax M2.5 searches to roughly 60 gigabits per second. Multiply that across a prefill cluster, and the aggregate data instantly fractures the capacity of any commodity Ethernet link. Model architectures are shifting away from purely dense attention toward hybrid designs. These systems interleave a few full attention layers with a larger number of linear complexity layers. Mathematically, this structural shift drops KV throughput by over 10 times compared to a dense model of similar size. The prefill phase still requires heavy arithmetic computation, but the physical memory state emitted by the model is now drastically compressed. With the cache size reduced by an order of magnitude, cross-data center transport enters the realm of mathematical plausibility. However, plausibility is not practicality. Hybrid models make commodity Ethernet feasible on average, but real-world request traffic is bursty. Raw network bandwidth alone cannot absorb those spikes without persistent congestion. This network map shows Prefill-as-a-Service, or Prfaa S. It connects a compute-dense remote cluster to a bandwidth-dense local cluster via commodity VPC connections. Short requests aren't externalized. Sending them across yields minimal acceleration while pointlessly congesting the network. The system applies a routing threshold, variable T. Short requests below T bypass the bridge to local prefill nodes. Massive requests exceeding T traverse to the Prfaa S cluster for heavy compute, compressing into a KV cache packet that streams back for local decode. This selective offloading ensures the compute-heavy hardware is reserved strictly for requests that actually benefit from remote acceleration. Yet while selective offloading filters out inefficient requests, it does not adapt to the continuous fluctuation of network capacity over time. To balance these offloaded workloads against a strict Ethernet ceiling, the system relies on a dual timescale scheduler. This dashboard tracks its two primary metrics. The short-term trigger acts on real-time network congestion. When the egress pipe hits its maximum capacity, the scheduler automatically adjusts the threshold T upward. With a higher threshold, the system physically chokes the flow of requests sent to the remote cluster. Bandwidth pressure drops instantly, and the system avoids dropping active connections.
The long-term trigger handles persistent shifts in overall traffic volume that create imbalances between the prefill and decode stages over hours or days. In steady-state operation, the aggregate throughput of the prefill stage must exactly equal the aggregate throughput of the decode stage. If compute outpaces memory bandwidth, the scheduler detects a rising decode queue depth. To resolve this, it dynamically converts local prefill nodes into decode nodes, clearing the backlog. By managing short-term network spikes and long-term hardware allocation, the architecture bends without breaking, locking the system at peak throughput. This routing logic solves the compute allocation, but it introduces a storage challenge, ensuring the system never redundantly transmits KV cache across the data center if a request relies on previously processed context. The hybrid prefix cache pool manages the two distinctly different types of cache created by these models simultaneously. The full attention layers produce cache that allows for partial block-level matching, but the linear layers produce recurrent states that are request-level. They demand an exact length match to be reused. Think of this like constructing a massive toy castle across two separate locations. The standard base plates are the full attention cache, acting as generic building blocks. The custom minifigures represent the linear states. These are unique, single-purpose pieces tied exactly to one specific request length. If a new query arrives and the remote data center holds a matching baseplate, a prefix cache hit, the system doesn't waste bandwidth rebuilding the entire castle. The remote server executes only the net new computation, building the custom minifigure, and transmits just that tiny addition over the network. A global KVCache manager tracks the physical location of every baseplate and minifigure across both data centers to execute this logic. By ensuring only net new information is transmitted, the hybrid pool drastically cuts the bandwidth tax associated with processing long-context, multi-turn agentic workloads. We can examine the impact of this architecture using telemetry data from an internal 1 trillion parameter hybrid model deployed in production. Processing a 1 trillion parameter model across geographically separated clusters is exactly the scenario that traditionally saturates a network and breaks the pipeline. This table outlines the deployment. Based on the model's profile, the scheduler locked the routing threshold strictly at 19.4K tokens. At this threshold, the system routed the 50% most compute-heavy requests to the Prfaa S cluster. Compared to a homogeneous single data center, this cross-data center configuration achieved 54% higher overall throughput. By moving massive requests to specialized accelerators, 90th percentile time to first token dropped by 64%. For the end user, this translates directly to faster response times on highly complex, long-context queries. Externalizing compute across a standard network bridge demonstrably improves local latency, as long as the routing is mathematically optimized. The final metric is the actual toll on the commodity Ethernet link during this 1 trillion parameter test. The aggregate KVCache egress load streaming back from the remote cluster measured exactly 13 gigabits per second. At exactly 13% utilization of a 100 gigabit pipe, the bandwidth wall is no longer the binding constraint. The combination of hybrid model compression and precise scheduling moves the bottleneck back to the hardware itself. Infrastructure engineers are out of the RDMA prison. By decoupling prefill and decode across different data centers, you scale compute and memory independently, placing hardware exactly where it makes economic sense.